Society has changed rapidly in really a short amount of time. It wasn't that long ago that most of us, when we went to work, this is what it looked like. Working in the land, usually focused on survival in planting food and habitat. And today, most of the population really, around 50% of the world, when they go to work, it looks more like this picture on the right. A huge, densely packed number of people. And our habitats, our houses, where there used to be small cottages separated, mostly maybe in small villages, now are densely packed together in these cities, which fits I don't know how many thousands and thousands of people, tens of thousands of people sometimes in a kilometre squared, which would have been just a family before, or a couple of families. This urbanization and great densification of the population in the world, it brings challenges to society, challenges that the whole world faces together. I think you know what I'm about to say. It's been on the news a lot recently, an environmental challenge that we all face together. You've probably guessed it right. It's sewage. Sewers, right? You never think about it, but at least in the UK, they were never designed to deal with the amount of sewage that is needed today for such a city with such a huge population. In the UK, we designed them with Victorian eras. I mean, we don't even know what's down there, and they are flooding quickly. When a pipe breaks and bursts underground, like so, it starts leaking everywhere. Sometimes they get blocked with whatever the hell that stuff is, and so they can have huge fractures in them. And it's very difficult to repair them or to stop this from happening, and things are just getting worse as time goes by. Whenever we want to repair them, what we have to do is we have to dig up the earth, dig up our roads and cities, and just have a look below and just see try to track where the leak is. It's really difficult to do the maintenance in this situation. Let me show you a little bit of a summary video of the situation in the UK, so let's see if this works. Yeah, so there's 750,000 kilometres of sewers and pipes in the UK. Every time we need to fix one, we create a huge traffic jam, we have to dig up the road, and if anyone's ever been stopped in a traffic jam like that, they know what a pain it is. The amount of street works causes a huge amount of cost, not just in the cost of traffic and workmen, but air pollution as well. And one of the main problems is that things are not getting better, they're getting worse. Our sewer infrastructure is getting older and older. It was never designed to last that long. We don't even know what's down there. When there's excess rainfall, we often get discharge of sewers into rivers and to what would have been, water that is supposed to be clean. The amount of water that's lost to leakages underground in this complex network we know nothing about is tremendous across the world. Think of the water problems that we'll be having in the future. We lose so much water in pipes and just leaks. So here's an idea. What if we design little robots to swim around in the pipes and find and problems and map out the pipes to begin with, to have a real good idea what's down there. These robots would swim around freely, looking for problems, mapping everything out, and when they find a problem, they'll communicate it back to each other, creating this network of information. So pretty cool, huh? That's what engineers are for, making stuff like that. So we have this idea of these robots mapping things out, but it's really dark down there. We can't add lights everywhere. We don't know how to create a map. So the next challenge now, okay, let's say we want to build these robots, how will they work? So what we've done is we turned to the animal kingdom for inspiration. We've gone to an animal that is very good at navigating in the dark. And again, this BBC clip really helps explain how awesome bats are at doing this. Have a look.
But like us, most of the insects it hunts can't hear ultrasound.
Looking for its tasty snack, flying around.
As the bat homes in, its squeaks speed up.
It means it's noticed there's something there. Something tasty. It's going in. Oh my god. what I learned from this video was not to be an insect flying around at night near creepy churches. But other than that, I also learned that bats are really good at navigating in the dark. And that is basically the power we want to harness. We want to harness that skill for our little robots in the sewers. So it got me thinking about that and like, how do bats do that? So to help me understand things like that, what I tend to do is I tend to do a simulation, and I've put together a super sophisticated simulation for you today. I want to show you what exactly the bat is doing. So you see I have my bat here, tasty insect. In the middle, I'm going to have a tree. You can tell that it's a tree because it says a tree. So here, every time you see these white lines, this white circle expanding from the bat, that's the sound it makes. So we're visualizing the sound with color. And you notice that the sound, it bounces off the tree, it goes through the tree, it goes around the tree, and the bat's just flying around looking for its tasty snack. I wonder what I'm going to eat today. And now the first reflected sound comes back to the bat. You see, it hits the insect and it reflects back. It catches the reflection, it knows there's something there, it starts to squeak more, it goes in and it gets its tasty snack. So that's how it works. I mean, you've probably heard of it before, echolocation. It just reflects sound off these objects and it listens in with its really clever hearing system waiting for the reflected sound. And by the amount of time that it takes the sound to come back, it can judge how far the insect is. Cool, huh? I'm just going to freeze on one of the snapshots here. If you notice, if we just freeze one of these images, the sound actually goes into the tree quite well. It kind of propagates into the tree, and you can even go around the tree quite well. Why is that important? Well, if it was trying to locate the insect with light, like we do, we see things using light instead of sound, using light rays, then those rays, they don't really go around objects and they don't propagate through, they don't really go through water or solid objects like the tree very well. They might reflect a little bit off the tree, but mostly they just die there, and then the bat could only see what's exactly in front of it here, rather than get a much better view of everything around that sound would have. So that's a little bit on the physics side. Right, so we've got these cities, we've got these sewers. We want to put these robots down. We know they're going to use sound, and they're going to just, be pulsing this sound and listening for what reflects back. So we want to use that to detect flaws in the pipe. If the pipe has a gap in it, sound leaks through. Maybe if it's blocked with something, we need to be prepared for anything that we might find down there. So how are we going to do that now? We know we're going to use sound. I'll show you how we might approach figuring out how the reflected sound works in these different things. How's it going to do that? So here's a scenario. The robot's kind of beeping these sounds, and here's an object. So a sort of engineer or even a physics approach to this is first to solve the simplest case possible. So I'm going to show you how that works. First of all, the rubber ducky is a bit complicated, so let's not consider the rubber ducky to start with. And that sound source is a kind of complicated too. It's got a funny kind of curvy shape to it. Let's start with something simpler. And walls can also complicate things. So let's start as simple as possible, but that is really how science works. We build up from the simplest case. What is the simplest case? The simplest case is a sound that is very flat. It's the simplest to describe with a bit of maths. And it's flat and repeating always the same note. So by that I mean if you were to hold a note, if you could sing, it would, I can't, but it would sound something like holding one note, it goes up and down. That's the simplest to describe. And then the simplest object to calculate how sound reflects from it, how sound interacts with objects is a sphere. So let's start with a sphere. So you see I've already solved this scenario. Well, what does it take to solve something like that? Well, it takes a bit of maths. Have you ever seen trigonometry and triangle-y stuff and calculus? I don't know if you've ever heard of those things, but that's what it takes. It takes a bit of work, but it's doable. The human mind can conquer this case of one sphere with sound. So that's where we start. And although it takes some work to do that case, once you've done that case, it's not too difficult to do two spheres. Because if you've done one sphere, doing two spheres is kind of like doing the same thing twice. So if you can get a computer to do one of them, you can get a computer to do two. And once you've done two spheres, you can do four spheres. And once you've done four spheres, before you know it, you've solved the rubber ducky problem. Because all you need to do is put spheres that basically fill in the shape of the rubber duck. And this will be how sound interacts with the rubber duck. Cool, huh? Start simple, work your way up. And once you've done one note, you can do lots of notes together, which form what we call an impulse. And just to have a look, this is what an impulse looks like when it reflects on the rubber duck. I call this the quack of the duck. Here comes out the quack. Powerful quack. Right, so, okay, back to a pipe. So now, the way that we do a pipe is we just fill the wall with lots of little spheres. If you fill little spheres everywhere, then you just do the same calculation we did before. We know how to do one sphere, we know how to do two spheres, we know how to do loads of spheres. Just get the computer to repeat the calculation over and over, and that's what you get here. So now we've got sound trapped in a pipe, and this is how it interacts with the rubber duck. We can repeat that same idea for more complicated things like starfish. Starfish are the nemesis of UK sewers. They just get stuck everywhere, come in from the ocean, they think they own the place, and we want to find out where they are. So here you see that the sound escapes above the starfish. It kind of interacts quite strongly with the starfish's legs, and if we put a little robot here listening to the sound that comes back, it would be able to identify it quite well. So at the end of this presentation, I'm going to have a little game to play. I want you to help me help the robot figure out what's there. What we're going to do is I'm going to show you a portion of a picture of where the sound is reflected, but I won't show you everything. And you have to draw lines, like blue lines wherever there's blue lines here, and white lines wherever there's white lines here. You're going to try and guess where they are to figure out the whole sound pressure field. This is the kind of thing the robot would have to do. So the question is, are you a good robot? We'll find out at the end. And one of the challenges you do will be to find out this scenario. So if you take a quick look now, and we come back to it, you're going to have to help me draw this without seeing the whole picture. We'll get there later. Okay, so another scenario that makes sound really good at locating objects is if the pipe turns a corner, right? It's changing direction, it's going somewhere else. If you were to put a camera or light, you wouldn't be able to see around the corner. Obviously, we can't see around corners, can you? So if you had the little robot with a camera, it wouldn't see around corners either. But sound sees around corners really well because it propagates all around the corner, it hits the starfish, and then it comes back. Compare these two scenarios. Like in this case, the end of the pipe does not have a starfish, and the case on the left. And the case on the right, there is a starfish. Notice that the sound field near the robot is really different in these two cases. So by just listening for the robot, just listening to the sound, it can really tell the difference that there is the nemesis starfish is close by around a corner in this case, whereas here the pipe is clear. So it can do this, and it can work for hundreds of meters, maybe at least 50 meters, and know that the pipes are clear. In this case, it would be able to know that the pipe was blocked. So can you help me figure out if the sound of one of these pipes is blocked or not? So I'm going to show you two scenarios, and we're going to try and figure out which of them is blocked and which of them isn't. So here's the top case, and here's what the robot listens to. Kind of creepy, right? Let's listen to that again. Okay, so now that's a scenario that the robot has sent some sound, it's reflected back, and you're trying to help it figure out, is this a blocked pipe or not? One of these is a blocked pipe, one of these is empty. So let's listen to the sound from below now. Okay, let's do that again. Get my form of techno here. Okay, last time the top one, then you're going to vote. You just choose which one you think is the blocked pipe. Okay, make up your mind. Is it the top one? Is it the bottom one? Are you a good robot? Let's find out. Which is the blocked pipe? It was the one at the bottom. So let's listen to that again. It's got that little extra da-doom kind of beat to it. So if you guessed that right, then well done, you'd make a great robot. If you guessed it wrong, then you know what? Maybe your career is not going down into sewers and listening to sounds that get reflected from rubber duckies. Maybe it's just not for you. I don't know. But it's quite difficult to tell the difference. Did you notice? Even for something, even when you look at the sound field, the pressure field in these two, they look really different. But listening to it was difficult. So the way that we get the robots to do that is we use pattern recognition. So if you've seen in the news probably AI, machine learning, it's kind of the same thing. We basically use pattern recognition to help robots identify when there are rubber duckies and when there are not rubber duckies. And what is pattern recognition? Well, it looks like this. You sit in front of a computer, you do a lot of maths and programming. So if you want to be part of the AI revolution, programming and maths, I'm afraid that's the way it is. And I think it's great fun. So we've explored how to get robots in pipes and figure out their problems, but there's more than just there's pipes everywhere. There's pipes for our infrastructure for oil and gas and water in different scenarios, and we need those pipes burst as well, and they leak and they get filled, whatever that is, and I no longer want to have lunch because looking at this. Okay. And the same lesson applies to not just pipes, but our infrastructure. We're building bridges and buildings and planes and underground networks and all that stuff that can crack, can degrade. And so we need to be able to know when it degrades, when a problem has occurred. We need sensors like using acoustics and everything. And that involves maths. And that's what maths look like. That's just some maths formula that you might learn at university. It's really cool. And coding, and this is what coding looks like. And really, you know what? We just need more people who are excited about this to help, check that our infrastructure continues to work, make things durable, make things last. And these are the skills that you need for that. So we need your help. So if you'd like to join in the University of Sheffield, let me know. I hope you enjoyed the talk.